Today, we're going to explore software engineering in the era of AI. I've shared some of these thoughts before. It'll be exciting to share them again. We're going to talk about the mega trends that have been going on in. Actually, I'm talking up to this camera here, aren't I? We're going to talk about the mega trends that have been going on in the tech market for the last couple of years. We'll talk about the underlying principles that make a great engineer that have only become more important in this era. We'll talk about, okay, what are the mega trends in terms of the technology capabilities in this era, particularly the rise of, I guess, models, language or other, but models that allow us to integrate unprecedented level of prediction into our applications. So there's this word stochastic that captures some element of the probabilistic take that you can now start to apply to software. Historically, if you're building software, you're like, hey, do this, then that. There's a lot of problems that you can't solve with that lack of nuance. Once you're dealing with a kind of problem set that you can need, where you need more uncertainty to be captured in the product. Think if you're giving legal advice, healthcare advice, you need to be able to acknowledge those aren't if this, then that. They're more like, hey, here's a potential approach. Then you are able to, if you're able to build software around that, it can open whole new doors. That's what we're going to talk about today. How do you, what are the underlying mental models for that? What are the underlying technologies? But it's all going to come down to prediction. Then we'll talk about what does this mean in terms of the workflows and team structures that you will be working with as software engineers in this era. Okay, there we go. But before we get into all of that, we are going to talk about Codesmith, because that is the organization that, I guess, supports all this, all these workshops. So Codesmith is designed to build out the platform from which software engineers can emerge who are ready for this sort of era. So that's my favorite example is a recent graduate. In fact, I think they are probably tired of me referencing their offer, but the job they got was a software engineer, legal prompter, a software engineer, lawyer. That stuff is game-changing. That's the future of engineering, the future of jobs, where you are building the kind of technology and software that previously you couldn't tackle, but now you can. But when you do, and you start building apps that make predictions around legal advice, you need the people building that. You need the builders, the engineers, the software engineers. They got to understand the predictions that are being made, as well as the ability to build that software in which those predictions happen. That's not like the PM who needs to understand the recommendations. That's not even the data scientist who definitely need to understand that the predictions, the legal advice being predicted by the LLM is decent, but also the builder. The actual software engineers got to understand both the predictions, are they good, are they bad, and the software, the ability to build it, the software itself. But this is what's happening, a boom in the type of problem space that can be tackled with software. It ain't just, by the way, the rise of AI, ML, it's also the rise of a whole bunch of other things. The software-defined things that previously were hardware questions or infrastructure telecoms questions. 5G rollout was the first telecoms rollout, network rollout, where the most interesting and difficult problems were not actually always being solved by the engineers, the physical engineers, but also were being solved at the software level, off-the-shelf kind of non-bespoke hardware for the 5G rollout, but then the actual problem solving, a lot of it happening within the software layer. Robotics. Robotics is exploding, especially, I guess, intelligent robotics is exploding. Much of the development of robotics is handled in a simulation environment at a software level. John Deere, the tractor manufacturer, has more software engineers than it has mechanical engineers. That is remarkable. Has more software engineers than it has mechanical engineers. The New York Times has more software engineers than it has, well, sorry, hires more software engineers than it hires journalists. So these things are evolving really fast. Codesmith is all about building those sorts of engineers. How does it do it? we'll keep this very quick here. How does it do it? It does it via underlying capacities. The tools are changing fast enough in this field that your ability to problem solve any new problem, take on any new task, and work out the tool for the job is vital. So that problem solving, technical communication, an approach to engineering that's based on principles as opposed to purely implementation details. And then how do you work with others, that non-technical, and then sure, the tools itself, the domain knowledge. Okay, we're almost done with the Codesmith stuff. To get into the program, well, there's a shorter version of the program and a longer version of the program, a part-time and a full-time. If you're preparing for Codesmith, know that the goal is that you could get some sort of developer role, whether or not you ended up going through the program, just by using this kind of preparatory material. I don't think I said the word preparatory for years. Preparatory? Prep material. And then post-program, you want to be targeting an engineering role where you are autonomous. That means you are not, you are able to take on any new task, whether or not you've worked with a tool before. That's the goal. Or start your own thing. So how does it do it? How does the program do it? Through 3 pillars. One, a pedagogy that is actually not very original. It's just like what I got at my... Oh. A pedagogy is not very original. It's like what I got at my college and university. And in fact, there's a great post on Twitter by someone in the engineering community who's got a mentorship program that's super regarded. And they said, hey, excuse me, Codesmith, Will, the pedagogy you describe is no different to my University of Toronto engineering program. And it's like, I hope so. That would be the dream, right? The dream is to have that timeless teaching style that enables you to grow, to learn any new thing. But you might as well do it with the most contemporary technology. You might as well do it with the latest libraries, the lang chains, the latest mental models, the LLM mental models. You might as well do it with TypeScript. You might as well do it with Docker, with containerization, things that a traditional engineering degree might not have. And you get to do it with a group of people that come from all walks of life. Yes, the Stanford PhD. Yes, the person who's just been admitted to Stanford. We had a nice application from a couple of days ago from somebody who's starting Stanford in the fall and wants to do the program before they start. Okay. I mentioned Stanford because it's kicked me out. No, not kicked me out. You have to get in. Turned me down 3 times. There we go. But also alongside people with a whole range of walks of life. So we won't dwell on these, but what's it look like in practice? That pedagogy is documented all here, but it means you can come out of the program doing whatever language you choose. You are not a React dev. You are a software engineer. In fact, we have alums in the room here who went out of the program doing Java, doing Golang. That's kind of the point, right? Like you want to be able to be flexible to the tools. The technology evolves, but you might as well use the latest tools. Alex, one of the co-founders of Codesmith on the faculty, ML lead at Amazon's autonomous vehicles division, complex place to work. Had an accident a couple of weeks ago, like a complex place to work. Wrote the book on deep reinforcement learning, all about how this quote, Codesmith prepares grads for the intersection of engineering with the latest workflows. They get to build interesting open source tools in that space. Community is a special above and beyond supportive community. This is my favorite thing here. Sure, I really admire these schools a lot, but I also admire, the person, especially if they get into Codesmith, who has taken a different route. Not in a kind of patronizing, oh, how great, but literally there are a range of routes to take to achieve interesting things for yourself and for others. Okay, and then obviously number 1 major is computer science, but there's a whole range of people coming into the program. And that produces outsized outcomes, not in terms of dollars, people, but in terms of the kind of creative work they're doing. Here's our software engineer lawyer, the job description requiring lawyer and software engineer. Senior analytics, these are all in the last year, right, or so. And then your conventional Snap software engineer, right? But there's all, I love this, Gabby was a math teacher before Codesmith, and now she's working on math teaching software. That's what you want, right? You want the people building, we talk a bit, I'm watching our lovely friend Sam Altman start to get a little bit of kickback for maybe the move fast and break things Valley attitude, which we know is part of what moves things forward, understandably, but you also want the people building your tools, your software, you want them to understand having lived software being done unto them. not just always wielding it upon others. And to me, that's the real notion behind having the Gabbies building math teacher software, because damn, you bet that they know what it's like to be on the receiving end of bad software. And given much of our problem solving is done through this lens, increasingly nowadays, damn, you want to have the people building it and leading it reflecting the users. That's my, that's what I want to do. I don't want to be another, or in my case, I don't want to be another BS trying to run an organization and not having built with the stuff that is the core essence now of change. Okay, so we don't need to talk anymore. If you're trying to enter the program, there's a big free community. You probably won't get in first time, but there's lots of support, hours and hours of support on it. But let's now dive in. Sometimes I get to co-host this with an alumni advisor or career support engineer who can answer your own questions about your careers. Nobody today, unfortunately. So it's just me. So as you have questions, throw them in the chat. If you don't feel comfortable asking them of everybody in front of me, in front of everybody, then DM me. I think the chat is open for you all to message. Oh no, sorry. Here we go. Now the chat's open. Feel free, people, to, if you get an unpleasant message, I'm so sorry I have to say this, but we had some people putting out some unpleasant messages. If you get unpleasant messages from anybody, message me and tell me, and we will boot them from the session. Okay, here we go. Thank you, Fern. Exactly. If you get any unpleasant messages, let me know, because all right. I'm excited to jump in now. No further ado. Here we go. There's me. There's my lovely nephew. There's my wonderful sisters there. And that is it, because now we're going to dive in. So hopefully it is interesting. I've got this camera up here, which is where but I am used to looking down at all of you on the screen. So who knows what it's like with me looking right up at the camera. Maybe it's weird. I'm going to try and look. Like you look in the mirror and you want to try and see your eyes looking directly. I'm going to try and look, and the latency is good. It's not bad enough. It's bad, but not so bad that I can see myself looking at the camera. I can't tell. Maybe it's weird. All right. Yeah, here we go. So let's, you know what I'll do? I'll close myself so I know that I'm looking right at all of you. Okay. Software engineering in the era of AI. New tools available, but also a new scale of challenges. Kind of badass. Happening at the same time. Some mega trends have driven that. We'll dwell on them briefly. It's going to turn out that it hasn't changed what makes a great engineer. As our friend Michael, person who runs this great mentorship program, themselves said, that ain't changed. And it hasn't. Engineers have always been about the ability to understand how to implement in complex systems, technology, infrastructure, mechanics, how to implement in that with a deep sensitivity of underlying social, human, societal, company, government need. They're working in and out to solve a problem for people. It's always been that. That's not changed. In fact, it's only going to get more important in software engineering as the problems being tackled become closer to our own identities. Things like healthcare, things like law. So the core capacities, PS and TC, this is problem solving and technical communication, those are only going to get more important. However, there's some new mental models, specifically mental models around how a model works. What is this notion of prediction, particularly around large language models? That is to say, particularly around prediction of words and streams of words to be used and understood by humans. What does that even look like? Building the mental model. We won't go all into that today. Actually, exciting news for everybody. Codesmith's kind of expanded, like Codesmith is designed to give you the capacity to learn any new tool. However, I do think it's worth having the mental models of the overall domain. Those are the hard parts of programming. That's the asynchronicity stuff. That's how the web works. Those are all things that are pre-Codesmith now to get into the program, to make sure you're coming in at this good level. But I would say the modeling stuff is a sufficiently new domain, LLMs, model pipelines, AI, that it's worth having the mental models of those pre-programmed. And from a couple of weeks from now, there will be the new hard parts of LLMs, hard parts of modeling that prepare you for the program and the units in the program about the implementation of those. Okay, so there are some new principles to develop, which actually, as I say, will be part of the hard parts free workshop cycle. So look out for those. Then we're going to dive into if ML AI is prediction as product, prediction of pixels, prediction of data, prediction of words as a product, as a user experience. Well, let's build the mental models around that. From predicting user choices to paragraphs of text to pixels. And as we know, some wild emergent abilities that let's be excited about. They're going to open whole new doors for what we can do. However, they got to serve us, the users, not them, the tech overlords. Because I say that tongue in cheek, but actually, honestly, it don't always go well. You know, and I'm not some revolutionary by any means. I do believe in incremental responsibility for every person who can engage in that space to do so, hopefully with a greater degree of concern for the user. That's fair enough, I think. And then we'll talk about what that looks like for teams. Let's dive in, people, starting with some backdrop that I think guides a lot of the rise of these new tools and technology. Tech recession 22-23. My goodness, if you see offers in the last month out of Codesmith, it must be. I mean, I talked to Annie, who runs outcomes today. She's like, look, I'm seeing some people who can't keep up with the number of things happening, interviews, whatever, and some who are not getting traction at all. So I thought that was interesting. But like, if you look at the offers of the last 30 or so, there were 3 below 100. Now that's something that was not reflective of 2023. So look, maybe we're finally really starting to see a coming back of the market. But 22-23, widespread layoffs, heavy slowdown, trickle down effect into the rest of the market when the big tech firms slowed down. There's optimism to be had for sure during that period. Most found new roles quickly. Layoffs were primarily not software engineers. And here's what I really want to talk about. The only reason I'm bringing this up is the rise of mainstream tech, formerly what you'd call non-tech. That is healthcare, finance. These are areas that previously were not being tackled as a technology problem as much. Now it's increasingly mainstream. And that means new scale of problems. If you're trying to integrate a healthcare system, my goodness, no existing tools are good enough for that. No existing workflows for software engineers are capable of enabling to work at that level of complexity, of integrating a healthcare system. My friend, his partner, she is an ER doctor in the Georgetown medical system in DC, and she's on their digital advisory committee as they try to digitize. It's just enormously complex to work on that kind of nuanced, uncertain, probabilistic, complex integration problem of software in those settings. Thank goodness we're going to have some new tools. We have new tools both for engineers, co-pilots, maybe AI agents, and in terms of the things that can be built as products. It's very exciting, but it requires a new evolved type of engineer, one who is even more committed to working out what tool to solve the problem with, one that is even more committed to communication of the technical stuff, because you've got a bunch of people helping you build out the healthcare software. You better understand how to explain it to them like they're 5, 12, well, I don't like that comparison, like they're a student, an undergrad, or a PhD in technology, in software and engineering. You better be able to communicate at those different levels. That becomes even more vital, and you better understand these new domains. So let's jump to that quickly. I don't want to spend any longer on this. Here we go. Problem solving and technical communication, even more important, but we have some new tools. So these are 5 things we've always said matter at Codesmith. Problem solving, technical communication, ability to take any complex demand from the engineering manager, from the user, from the hospital system, from the lawyer, from the entrepreneur, from the principal engineer in your team, from the senior software engineer, and turn it into an output. turn it into a solution, turn it into something built in software, in tech, with likely code. And then the ability to explain it. It's even more important because the tools are changing so fast. You need to be resilient to that and work out whatever the right tool is for the job. You need to say, oh, LangChain. Okay, let me start implementing an LLM directly to build a chatbot in my application. Great. What is going to change? Engineering approach and principles. There are some new mental models, people. We're going to see them a bit today, but look out for the hard parts workshops on these in the next few weeks. They go live in the next few weeks. Being a good communicator, a thoughtful, non-technical communicator, no less important. Domain knowledge, some new implementation details that are built on these mental models. Some are really built on typical back-end and infrastructure engineering stuff, like model deployment. Questions about that look a lot like questions about deploying any application. Questions about deploying an API, that's a place at which, if I'm opening, we'll see the example. My favorite example is lex.page, but let's use a different one for a second. If I'm using an AI app like Suno.ai that allows you to prompt it and it produces a song in response to that prompt, I love it. That will have an API endpoint. That is when you write your prompt, rock and roll, I don't say rock and roll, I don't know, Chuck Berry style song about Henry VIII. I don't know. That's a lame example. It will then send a message, an HTTP message to an API endpoint. That's just a URL that can receive data, the description. It will then return back, hopefully, the MP3 to be played. Well, there's a whole bunch of pre-processing, post-processing steps there, but that's API design that you as a software engineer are really well positioned for, but equally works hand in hand with the ML engineers. But there's some new stuff there as well. And then co-pilots, automated testing tools, agents, and even libraries like LangChain to rely less on the ML engineers to do the integration yourself. Nice quote here from one of the Codesmith faculty. Practical application of AI ML, unlocking greater effectiveness, accomplish the kind of problem solving at a new scale that wasn't possible before. So let's now dive in. We're now going to explore together, people, prediction. What are, if the key thing is ML and AI is productizing prediction, from predicting what item a user is going to buy next to predicting paragraphs of text that best provide an answer to a user's question, to predicting a collection of pixels based on a user's prompt, that's an image, to predicting a stream of changing pixels in response to a user's prompt, that's a video. And even with emergent abilities, things that you couldn't expect from the raw data to have happen, as we know, the ability to translate words that have never before been translated in the raw data set. By the way, that was the underlying motivation for the transformer architecture originally, was efforts to try and capture meaning of language in one language with meaning of language in another language, where even if there wasn't a like-for-like corresponding word previously translated, its context could provide insight on what the translation could be, probabilistically could be, but that is where we're going to dwell for the rest of the talk. So I want us to actually start to get a sense of this prediction. So here we go. We're going to talk prediction based on previous patterns and data, the essence of prediction. That's what gives us the evidence to make a claim about the future. Then we're going to talk about doing so without causing harm. If you're using old data, as in like from the past, you're bringing data is collected by humans. Data has all sorts of choices and categorizations and classifications and inaccuracies from humans. If you're then making predictions off them, relying on things you learn from that, but now automated, these predictions are automated, right? That's what's so powerful about them. You might implicitly cause real harm. You don't want to do that. Prediction based on predefined categories and predictions based on seeing what the data looks like and identifying categories. Prediction, at least in some sense, this is the most transformative domain, neural networks, some sense based on aspects of the brain's own architecture, and then doing so particularly with words, and then with whole paragraphs from which emergent abilities come, and then doing so with your own data, fine-tuning, and then doing so with pixels and even streams of pixels video. We'll see they all extend in a long trajectory of using patterns in existing data to make predictions about future scenarios. Okay, so let's start with, and please throw in the chat, people, your own questions. I'm not seeing many questions in here. Okay. Please, people, throw in the chat your questions about the material, your questions about given models, and I'll look forward to diving into those. Okay, let's do it. So starting here with prediction based on previous patterns, known as a model. This is the core of the data scientist role, to take existing data and identify patterns in it using different approaches, models, different techniques, models, to allow you to make predictions about future scenarios. So let's look at a very specific example here. This is one I gave at a talk at Unilever's division Dermalogica, and so it has some of their products. So using existing data relationships, one that causes and the other that's a consequence. In this case, the cause is what items, or the implicit cause, actually, to be very fair, the term cause is not actually relevant here. It's associated. What are the patterns? We don't necessarily look for cause so much as is it associated. If you view these three items, oxygen cream, retinol serum, vitamin C serum, the item purchased 15% of the time is a retinol serum. Okay, we can now use that data, but actually thousands of users and the collection of their items they viewed and then the item they went on to purchase to best determine what item to promote to a user based on what items they viewed. So we take a huge log, think an Excel spreadsheet, you could imagine 3 columns, item viewed 1, item viewed 2, item viewed 3, maybe it's hundreds of columns, right? They've viewed hundreds of items, and then what item is eventually purchased. And we can then use a model that is testing out for every particular example which factor was most important in determining which item they purchased, which combination of items they've seen previously was most predictive, was most going to give you a clue for the next set of items, what item to show them from that set that will most likely then be purchased. That model, that set of relative importances, we're going to say that item viewed with that item, this item viewed with that item, the serum viewed with the, well, they're all called serum, cream, together, followed by this item, is most likely to lead to the second item being purchased or the 30th item view being purchased. And we can look at those and give different weights, different importances, literally percentages, importance, the different combinations of items viewed, and see which relative percentage importances we give most likely across all the different examples corresponds to the maximal percentage likelihood of purchase on every single example, such that when we take in a new user who's viewed item 1, 2, 3, 4, 5, and so on, we can determine most likely the item to show them that will encourage them to purchase it. We're using prior relationships in the data, input and output, input item and item purchased, to then determine for our new user which item to show that will be most likely purchased based on all the previous examples. That previous set of examples is known as the data we trained our model on, which sounds very fancy, but is just, we've given it those examples and said, work out if we attribute a lot of importance to this item and this item for these two purchases, these two users, sorry, does that undermine how reliable our prediction is for these two users? We've got to try out lots of different importances, because if we give lots of importance to this item combined with this item, and then yes, the user purchases it in that case, but the same combination doesn't lead to a user purchasing it in this case, we probably need to like offset those and give a little bit less importance to that combination of items. The model training is assessing how we can give different importances to all those different combinations that maximizes the accuracy of the prediction across all those examples. Maximizes how closely it relates to what actually was purchased across all those examples, so that for our new example, our new user, we can have the most likely item shown to them. Okay, that model is called collaborative filtering. uses prior users' collected preferences to infer, to make a prediction about a new user's preference, interest. Okay, previous patterns. An example that I think is far more powerful to most of us, because it actually does make our lives easier, predicting based on previous patterns without causing harm, DoorDash, Uber Eats, automatic refunds. This is something many of us would have experienced. Used to be that if your item didn't show up and you said you press the help button on Uber Eats, it was into a chat. Maybe they were quick. Maybe it was like, speak to you in 10 minutes. The rep will be able to speak to you in 10 minutes. Instead, now, in most of our situations, ask for refund, and it's like magic. It says, yep, refund. What the heck is going on there? That is the running of a model they built based on a lot of previous examples. So what are those previous examples here? Well, it's every time previously somebody made a request for a refund with a customer service agent. Oh, I'm rather on camera. Here we go. Request for a refund with the customer service agent, that in each time the customer service agent discussed it with them back and forth. Yes, sir. So you're saying it didn't show up, but the delivery person said it did. Or in some cases, well, we've spoken to the delivery person, they haven't responded. Okay, we'll give you the refund. When they did that, they were able to base that not only on the conversation with you, their judgment, but also maybe there are 100 pieces of underlying data information about your request that were relevant to the customer service agent's decision. Were you legitimately requesting a refund, or were you trying to get a free meal? And those 100 factors, they might have taken into account themselves when looking at your case, but also they took into account their own vibe of messaging you, whatever. But those 100 factors might have included things like, how old was your account? How many accounts are on that IP address? How many times have you made a claim within the last 6 months? How many times have you made a claim in the last week? What's your total spend on that account? How big was the item you purchased? How long after the item delivery did you complain? All these factors would have affected whether they gave you the refund or not. But they were deciding, or what's called labeling, the data, the information, all the information about you, the case. They were labeling it either fraudulent or not. Either you're trying to get a free meal, or legitimately the food didn't show up. That is our data that trains the model. Now, the model training period looks at, let's say, 100,000, maybe 1 million of those cases where we had lots of pieces of information. Again, think Excel spreadsheet, Google Sheet with column, 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 column. And at the top, you've got number of prior refund claims. 2, 6, 20, 0, 0, 0, 0. Account history, 12 months, 48 months, and other months, 0 months. Number of new accounts on IP address in the last 5 days, 0, 0, 0, 0, 35. Number of claims in the last 5 days, 0, 0, 0, 0, 7. Okay. And then the key column labeled, was it according to that situation when the request was made and talked to by a real person, legit or free dinner, fake fraud, trying to get free dinner. You got 100,000 of those. And this is where it gets really cool. The training of the model is attributing different percentage importance to each of those factors and the different combinations of those factors that allows you to take all those inputs, give different importance to them to maximize the likelihood that it matches what was actually the ground truth, what the customer service rep determined, was it fraud or not? Should they have got their dinner refunded, or were they trying to get a free dinner? And we can then attribute the model training period is saying, okay, this case, we had 35 claims on that account in the last month. Their credit history, their account history was 1 month long. And their spend previously, where they didn't refund, was 0. All those factors together, let's give very high weight to those, 100%, 100%, 100%. And does that predict it was fraud? Yes. And it was fraud, or at least the customer service rep said it was. But damn it, further down in our model, further down in our examples about raw data, our example data, you've got somebody who has a brand new account, 1 month old, let's say, who's never spent money on it before, but made a claim. They just had a really bad day. They were really unlucky. They didn't have 35 claims, but the other things were they had a claim and the account was fairly new. And the customer service rep said that wasn't fraud. We gave them the refund. But if we gave 100% importance for determining is it fraud or not to length of account being 1 month and spend $0 until today, when they then try and get a refund, that would be making the wrong prediction from our prior examples. So the model training is going, okay, let's not try 100% on that. Let's try attributing less importance to those factors because we don't want to mess up that prediction. We don't want that one to end up saying, oh no, that was fraud, when actually the customer service said that wasn't fraud at all. So our model training is taking 100,000, 1 million examples and testing lots of different importances, lots of different combinations to see what are the right importance weights, percentage importance is given to the different factors that most reliably predicts fraud or not. And hey, if you're 95% sure not fraud, build a product around it. Automatically refund in that situation. For the 5% otherwise, go to a customer service rep. That stuff is game changing, and that's a very, fraud detection, a very pure example. 2 outcomes, fraud or not. Models trained on historic data to assess how important is each input and the combination of those inputs. Then for future ones, when the next user comes along, we can make an informed prediction on it. But here's the problem. We can't have that cause systemic harm. Those customer service reps determining, is this a legit case of food didn't show up or not? Those customer service reps, they're humans and they might come with their own biases. They might even say, well, hold on, I didn't get a good vibe from that person's request. A good vibe, that could very easily be a systemic thing that's maybe misaligned with the actual truth. It's not accurate. So, and that's when we're dealing with a refund on DoorDash, imagine it's dealing with healthcare diagnosis. Imagine it's dealing with legal advice. It's absolutely vital that as we build out these products, and this is not a new thing to say, ML and data science and even AI alignment and ethical decision-making is a mainstream topic, but it don't get any less important, especially when you're building entire products around it. So that's, vital that the data you're using is being closely assessed for the moral questions that it entails, for the decisions that are based on humans, because in future, you're going to be automating the prediction, automating the decision. Okay. All right. So let's see if we've got any questions. Yes, Rakib in YouTube chat. Shout out to our YouTubers. We're back on YouTube. How about that, people? Oh, maybe there's a different. There it is. Oh, not many people watching. That's for the best. It wasn't worth it for them. They know there's better out there. Oh well. Question from Rakib. Hi, Rakib. With the advent of LLMs, not LLMs, large multimodal models, how does the programming pattern change? What do you think will be the shift in software engineering? So this is particularly talking about the ability for models to make predictions, not just of text, of pixels, but even of actions within a complex system, actions within a complex engineering system even. That's really interesting. The ability to interpret maybe a system diagram, image, a mode of pixels, and determine actions within a bash scripting environment, typed interaction with computer, right? That's a different input and output of model. So let's look at that topic in a bit, Rakib. I think, we'll talk about it, but the scale of problems that, as I said at the start, software is starting to become the center of solving things like healthcare that have barely scratched the surface. It's kind of like, thank goodness that these new tools are going to be available. But just note, Rakib, these are tools where to implement them in that vastly complex technology system, you've got to understand the scope, the limitations, the possibilities, the dynamics of that technology system. That is not a product manager. That is a software engineer, someone who understands the possibilities, the how, the what, and the why. That may then involve saying, hey, automated agent, now go and try and implement, edge case. How are we going to handle that? You can't do that without an understanding of the scope in which you're building. That's exciting. That means a new scale of problems being solved that were never able to be solved before, but software engineer takes on a larger piece of that, takes on larger problems within it. So exciting, Rakib. I would stress that you want to have mental models of those LLMs, or in this case, multimodal models. Just to be clear to be what that means, these are different modes of data, different modes of action. So the data is not just input text, output text. The data is anything that's saved on a computer, I guess. The data might be actions to be taken in a engineering system, like Git, commits or otherwise, committing, putting down code. It might be looking at system diagrams and interpreting the meaning to then take steps within a system, or to generate bug reports, or to generate feedback on that system diagram. The modes are the different types of data you can deal with: imagery, pixels, actions within the system, text, code. I hope that makes sense. So great question, Ricky. Yeah, Johanna says, is this a systemic bias which you hear about, racism and AI? Yeah, absolutely. Where it might differ in racism and AI is, in this case, we're going to come to this right now, supervised or unsupervised. In this case, we were talking about labeling the prior situations fraud or not. There was a person making a decision, fraud or not. It's a bit more transparently, whether we apply blame, at least there is a degree of which a human has made a decision, and therefore, we better make sure that decision is good. Particularly in large language models, which can be both labeled data, that's where humans have labeled it, or not. There is also a lot of situations where it's not been we've just taken we're going to see this in a moment, taking the entire body of text on the internet. The bias there can be simply, just as bad, but simply the prejudices in the collection of spoken language of humans on internet. Nobody said, hey, make this choice, that was fraud, that was not. It can even just be people have in their general discourse implicit moral positions and or immoral potentially positions that are now baked in to the prediction of future text. So it looks a little bit different there as well. It may not even involve having labeled, having said, determined that was fraud or not, or that's a good decision or not, or generated picture should look like that or not. It's based on the collection of all generated pictures and the associated alt text, for example. One of the huge ways, there's a hugely important model, or models, there's a few of them, that associate text description with associated images and the collection of pixels of them. They use, captioned images across the internet as their source data. They use alt text, that's the text that when you mouse over an image describes it, as their source data. Well, you can imagine nobody in that has said, hey, let's make sure in future that guides our decision on what an image generated would look like. But it's certainly going to. So it can look, Johanna, even more embedded, even less determined, even more just like the collection of humans' views by the choices and words they've made in their action on the internet in the last 20 years. Doesn't make it better, but it is it's even more subtle. Fern says, should there be concern for those whose careers are impacted, artists, musicians, particularly in terms of plagiarism? Is there anything built into models to help prevent this? Oh, what a great shout. Look, Fern, I would really like to think more about this. I haven't thought enough about this because my major, nobody owns code, at least not code at a scale that is developed so far by software engineers. It's even often open source libraries, right? It's very much the solution to a problem. And so I've not gone like, oh my goodness, GitHub Copilot is plagiarizing a bunch of code. My biggest fear, until one figures out, we all are human, we all go, well, shoot, it can generate code, is my biggest fear is, okay, but now the scale of problems that can be tackled, the nature of those problems can evolve, and you see that with the kind of roles already being hired for build legal advice software, unprecedented, but now possible. Software engineer, Python 2 years experience, and must have law degree. So my focus further has often been on that lens, which is, wait, are we still going to have a bunch of builders? And the answer is yes. I haven't thought so much about the creatives piece. We actually have a great writer who works with us, who left being a writer, UX writer, like guiding how to communicate on a website, for example. He left being one for a while when ChatGPT came along and a bunch of his work got taken. But now it only raises this game of how high quality your communication has to be, because average communication, it's everywhere now. Average text, it's everywhere now. And so it only raises the game of somebody who is able to say, yeah, but what do you really want to say here? And, so Fern, I haven't thought about it too much in terms of, but it evolves. And it's a perfect example, this writer who works with us, Adrian, who went from being like, shoot, all my jobs have gone to ChatGPT to now even more in demand, because what that creates is an even higher bar, because humans are always looking for signals of quality. When the quality goes up, they use signals of quality as, is this worth my time? Should I bother with this company? Should I bother with this Codesmith thing? Is it good enough? Well, if it's generated by ChatGPT and you can tell it, which you can for now, then you go, well, there's no effort there. I ain't attributing much value to that. So you have to get even more finesse with your language, your communication, your way of speaking, that shows the audience this is something special. And if you look at the history of art, that is the history of art, right? The history of art is, well, technically I can literally capture the image imperfection, known as photograph. Well, then art becomes expression of ideas. So in terms of plagiarism, which I think essentially you could look at some of these elements as, I think that's going to be really interesting and going to be a major thing in the next 3 to 5 years, capturing the inputs that are contributed to these models that are going to make billions and billions, and trying to attribute some of that wealth back to the contributors to it. So great question, Fern. Let's take a pause on questions for now. Yeah, Varma, great question on integrating these into your projects. The best thing I can say on that, Varma, for now, is experiment with LangChain. That's the library to really go to one of their hackathons. I'll be honest. Typically, it'll be easier for us to speak to that, Varma or me, once we have, so the Codesmith, I'm really excited with this. Like, every bloody boot camp on earth, Codesmith's not a boot camp, but every boot camp on earth is like, hey, we're going to do AI in the program. I ain't going some lazy drag and drop nonsense into the program. I want people to have the ability to contribute, as we'll see what it looks like in an engineering team, as what I call, I'm not an ML engineer, but I'm not an ML engineer, but I can help you with all the pieces around it. I'm not an ML engineer. I'm not, expert in the math. I'm not even necessarily expert in the design of optimized GPU distribution of tasks than an ML engineer might be. But I've got to build all the stuff around that, all the stuff that integrates that prediction. I'm actually pretty damn good at that. I want every grad having that ability. The way that works is in Codesmith, pre-program, you must have the mental models, that in the program, you only have time to get a sense of the implementation details of those mental models. So in hard parts of programming, you learn mental model of functional programming, mental model of asynchronous programming, and implementing it a lot. And then you do React in the program that implements some of those features in a 2-day unit, 4-day unit, 6-day unit. Then you do an open source project. We do a bunch of regular projects that use those tools. Then you do an open source project that maybe takes you into an advanced part of software tool building. And then you go into the job. Okay, I want that to expand, and we're doing it. So pre-program, you build a mental model of LLMs and a model structure. In the program, you have multiple units on implementing, as a software engineer, as we just got asked by Varma here, ML and LLMs and other models techniques into your projects. And then, and this is most important, there is a wealth of opportunity right now to build open source projects, tools, libraries that are around empowering software engineers to integrate models into their applications, both in terms of their applications and their workflows. I cannot wait for the residents in the program to be able to expand the open source stuff they can do to build tools for that. So Varma, at that point, I have a ton of answers, ton of examples. For now, I can actually send you all. James wrote up the AI curriculum pieces. I can send you all that because that will give you a sense of the core pieces, Varma, that you need to do. I will send you that in the Slack channel here. Sorry, in the Zoom chat in a moment, but I'll do that in a moment. Okay, for now, let's get back to it. So, prediction based on either labeled data or not. Predefined categories or categories you identify by actually running the model and trying to cluster your data together. One's called supervised learning. This is where the prediction that your prediction model is a posh word for the ability to turn an input into an output, turn an input of user is asking for refund and has this history on their account. Is it fraud or not? The input, the output. The input is all that data. The output is, was it fraud or not? Automating that prediction. The model is the automation of that prediction based on all those factors. In previous cases, what was the most predictive of fraud or not? That's the model, the set of importances of the different pieces of data, history of account length, I don't know, credit score, maybe. These aren't great, right? Predicting output, fraud or not. Classification is labeled fraud or not. A class, a category of cases that are fraud, a category of cases that are not, and the percentage chance of each. Okay, for a new input, you can predict a class, a category, discrete, that means one or the other, not a continuous stream, or a value. This might be based on today's weather and other factors. Can I make a prediction about the stock price tomorrow of NVIDIA, for example? The model will look at all previous days, the day before and the day after, and determine what are the most important factors for predicting the weather tomorrow, such that today we can predict NVIDIA's stock price tomorrow based on factors yesterday. Such that today we can make a decent prediction of a value, not a category, although it kind of is, right? But it's a continuous category. In this case, is NVIDIA's stock price going to be, market cap going to be 2.7 trillion or 2.8 trillion? Good for them. That's prediction based on prior labeled data, because the examples, the inputs, the data we use to train, to inform the prediction that we're now going to make for the future, the data we use was previously labeled, either as a class, fraud or not, categories, or as a value, stock price or market cap on each day. So we have prior examples with an output such that when we predict now, we can make a prediction about a given output based on those prior examples, which were labeled, which were given fraud or not. Okay. Unsupervised learning. This, and a great example of this is, we have a machine learning data science research group associated with Codesmith, which had a bunch of PhDs who went on to become data scientists or ML engineers, and they did some fascinating work before. Their PhDs were in things like physics, or they were postdocs in physics often mostly, and they'd done a bunch of particularly unsupervised learning. So they had done things like at CERN, which is where they clash particles together, they have profoundly effective and powerful detectors for electromagnetic particles that, I guess, when you collide atoms, I don't know, they explode off. And those detectors, like electromagnetic calorimeter, I don't know, ecal, have extraordinarily complex and measurably large amount of electromagnetic particles that explode off. We don't have labels for them, fraud or not, good particle, bad, relevant or not, before we collect the data. What we do instead, for example, is run a clustering model, a clustering algorithm that looks at all of those collected particles and the data around this. I'm really hitting my physics limit, so please forgive me. But all that, when these things explode, they literally release like photons. These like I'm hitting my limit here. These are like light particles, and they get captured by this detector. These billions of values and more, we want to identify, are there patterns, for example, what's normal and what's not? Well, there are algorithms that we can run or models that can be trained on that data to determine, for example, let me get this right, can cluster draw, there's one called dbScan, which is what they often would use, that would draw together close points and then spread out those that are further apart. In doing so, identifying clusters, you can then give them labels, normal or not, identifying clusters within the prior data, such that when we run our model then on a future experiment, and off explodes the particles and they're trapped, we can see which ones are within the existing clusters. When we run the model, we pull the data together and see these in clusters, and which ones are not. That would be anomalies or even novelties, new things. But we don't have pre-labeled data that's fraud or not. Instead, we look for pattern shapes in the data. This is unsupervised learning. The model is not trained knowing this is one thing or the other. Instead, we apply to the data, the model, and identify clusters by even potentially tweaking the model to pull values together that makes them a cluster and other values not part of that cluster. We then can take new experiments. So notice the same two stages. Look at existing data, give the model that data to determine what are the most important factors, what are the things that are inside a cluster or not, and then for new experiments in this case, we can use that learning to run that now trained model that knows, this piece of data is in a cluster or not, is associated with other values or not. We can then run that on a new experiment and go, wow, these values here are novel or anomalous and do not fit our existing clustering model that has been trained on prior examples. That was my physics knowledge reaching its absolute limit. Okay, supervised, unsupervised. Now, oh shit, we're going longer than normal. I don't know why I'm going so long here. Now, I'm back to my camera here. Now, let's talk about making predictions based on the structure of the human brain, at least analogously. These are the algorithms, these are the models that in machine learning that have moved forward much of the work we do. There are absolutely other profound breakthroughs. There's a great Hacker News thread recently. All the excitement is around neural networks and particularly large language models and transformer-based architectures, which is a big part of neural networks. What else is going on outside of this area? What are the other breakthroughs? There are other breakthroughs, but we'll focus here because these have accelerated much of our experience and the ability to productize prediction, because the predictions with neural networks are very flexible to the kind of data they can work with. They're very flexible to very real human problems that are not yes or no, if this then that, but are nuanced, involve subtlety, like this one here, interpreting handwritten digits. So there are many algorithms you could run to try and look at a handwritten number and recognize what number was written there. But most of them have all been blown out of the water by neural networks. And actually, I had the chance to speak to a professor at my college at Oxford who worked on early efforts to capture the way that thoughts, ideas, and even language was structured without using neural networks in the 80s, working with the person who went on to win the Quimby Nobel Prize in computer science, the Turing Award, someone called Jeff Hinton, who invented or discovered or identified a concept called backpropagation that is vital to neural networks. So this work's been going on for decades, and it's all coming together partly because of the growth in computational power of the last 10, 15 years. So what's happening here? This data set is very famous. It's handwritten digits from 0 through 9, 70,000 of them it's called the MNIST data set, and it's National Institute of Science and Technology. It was done with USPS in the 80s, I think, as an effort to improve parcel sorting. Can we look at and automatically interpret the zip code? 90 whatever. Can we interpret the zip code? So what is a handwritten digit? Well, it's just a collection of pixels, light and shade. In this case here, we're just keeping it very simple. There's zeros and there's ones. There's black, dark, gray, or whatever, and then there's 0, white. In fact, incredibly unhelpful to me because actually the digit is white and the background is gray. Very unhelpful to me, but forgive me. So you can see in this grid of pixels, 0 and 1, and in reality, we'd probably have a whole range of grayscale, right? 0.1, 0.2, 0.4, 0. Whatever. And hopefully we would not just have a 5 by 5 grid, but maybe, in fact, the MNIST data set, a 28 by 28 grid. 28 by 28 is 700 and something. I don't know. 84 maybe, I'm not sure. But that's 784, whatever it is, features, pixels that are information for our model, for our testing of different importance of each feature to determine which of the collection of pixels is most important, which are the zeros and one. Think of it like a literal spreadsheet. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0. Which is the most important for determining is this a 9 or an 8? And in this, albeit simplified example here, you should be able to pretty quickly see that it ain't the top line. For this 9 and this 8, 0, 1, 1, 1, 0, 0, 1, 1, 0. I got no information there if it's 9 or 8. It's the same. But look at this bottom left-hand corner here. All light on 9, all dark on 8. My neural network is going to attribute greater importance to that area of the pixels, of the grid and of the values, as determining whether it's a 9 or an 8. But damn, there's another 28,000, wherever it was, I can't remember. No, sorry, 70,000, another 70,000 images of grayscale image of handwritten digits. There's another 70,000 of them. And in some cases, this bottom left-hand corner here is actually filled out with high value, dark areas for the number 9. The training of the model is taking all 70,000 of those images and their pixels representing them. You can see the 9 there and you see the 8 there. I messed up my 8 there. It should have a 1 there. You can see all 70,000 of those, and it's assessing, no, not assessing, it's testing little adjustments. Let's give a little bit more importance to that pixel. A little bit less importance to that pixel. A little bit more to that one. A little bit more to that one. A little bit less to that one. And then it's seeing, does it predict accurately, is it a 9 or an 8? And then it's doing for the next one with the same, give more importance to that pixel, a little bit less to that one, a little bit more to that one. Now, in practice, it's actually saying a little bit more to this collection of pixels, a little bit more to this collection of pixels, a little bit more to the collection of pixels. It's going to convolve or convolute. It's going to break out the image into sub-pieces and try each different sub-piece, which is a combination of pixels that most predicts, is this a 9 or an 8? But doesn't break all the other examples. Because damn, if we say, yep, if it's got ones here, it's definitely an 8. What if actually the handwritten 9 goes into those pixels as well? The training of the model is going to be testing all of those different importances, not specifically for each pixel per se, but for the area of pixel, for how we give importance to that area of the image, for determining what is the best set of importances given to each area of the image that best predicts for as many of those digits as possible, whether accurately it's a 9, an 8, a 6, a 4, a 2, a 1, a 0. Predicting pixels, predicting classification of a number based off the pixels. The training stage tries different importances for each pixel or combination of pixels. That's simplifying it slightly to see which maximizes the probability that the model correctly classifies the image as a 9, but you've got 70,000 examples of those. So you get one working really well, you break all the others. The training of the model is testing all the different possible combinations of importance that maximizes the prediction for as many of the numbers as possible. And that is why NVIDIA gets paid so much money, because you've got to try a lot of different calculations and they're little tweaks, percentage importances, which is why NVIDIA gets a lot of money, because they were the creators of the GPU, or not the creators, they were the power behind the GPU, the graphical processing unit that is super optimized and no one else caught up yet, super optimized for doing lots and lots, trillions, not even trillions, beyond numbers, Googleplexes of little tweaks. Tweak that importance, make that bit a little bit more important, make that bit. And actually, these neural networks have multiple layers which combine up these different pixel importances and try out new weights on different sub-bits of the image. A convolutional neural network will do that piece along with other approaches. But doing Googleplexes worth of little tweaks is exactly what a graphical processing unit does. I think I'm right in saying, I don't know this is that's what it does. But this is because games, to make them look really realistic, have to calculate lots of tiny little tweaks, tiny little calculations that are very simple. They're like, multiply this by that for tracing when you're in a game, the rays of light. If we're in any physical space, we don't realize, but the light is highly associated with our sense of realism. The light flowing in is, I don't know, trillions of particles of photons, and every one of them bounces off, and we can feel that realism. A game wants to replicate that, and it will literally need to map every single ray of light around the physical space in your game, and then you take one step forward in the game, and it's got to do it all again, or at least tweak it. Sounds a lot like a lot of tiny calculations, a lot like how you train a model here to try all possible combinations of the pixels and the importance of the pixels to get the best set of predictions across as many. You can get one of them, yeah, perfect. We know that if we give total weights, total importance to these pixels, and to these pixels here, the bottom left, for these two examples, it will 100% guarantee that if it's got zeros here, it's a 9. If it's got ones here, it's an 8. But we've got 70,000 of these images, and we want to try to maximize the prediction across as many of them as possible. Okay, you can then run that model on new hand-drawn pixel and give a percentage chance of each number based on all those prior examples. This is in your phone with image recognition. When you search dog on your iPhone in your photos, and it finds all the dogs. Because there are patterns of pixels in that image of a dog that are clustered together or different combinations that we can't even see. We don't realize that a dog image will typically have a particular association of light and shade, a particular association of values that we can attribute, the model attributes weight to, importance to, by seeing lots of pictures of dogs and lots of pictures of cats. We can't even see. Here I can see this little bit here, the 111 and the 000 is clearly the most important pixels. With a dog and lots of, I can't even tell, but the model can. The model's been trained on millions, potentially hundreds of thousands, millions of images of dogs, of other animals. And was it a dog or not? Was it a 9 or an 8? And then it's tried giving lots of different importances to all those pixels to a million images of dogs or 100,000 images of dogs and work out which is the best combination of importances to each bit of pixels or sub-collection of pixels that across as many examples of dogs and cats as possible gives the most correct answer. That's a dog, that's a dog. You look at it, that is a dog. Okay, that's a dog. Oh, but shoot, if we attribute a lot of importance to this collection of pixels over here, it says it's a dog, but it's not. Okay, let's try a different combination of weights. Those little tweaks and rerunning of that until you get the best possible prediction, that's the training of your model. That's why NVIDIA is so rich, because it involves a hell of a lot of tiny calculations, re-weighting, re-attributing different importance to different parts of the data. Okay, so the data, I said pixels being interpreted there, different parts of the pixels. What about language? Because I know what an image looks like in terms of pixels, that's how we see it on the screen, but what is language? Well, I'm going to do a break for the chat in a second, people. I know we're going horribly long here. Shoot, this is great news, by the way. This means I can't go to the gym. I had I had a commando which is like Barry's in Mexico City, booked for 6 p.m. here. Yay! I can't go. Woohoo! I was not looking forward to it. It's really hard because it's all in Spanish, and while I speak some Spanish, not enough to interpret what they're saying on the treadmill. And so I regularly, oh, here's a camera. I regularly have to interpret what's being said. And that is very difficult when you are trying to sprint and or not. Anyway, so I have learned though, piso, people on the floor, corredor, runners, and sigue así. No, sigue así. Keep going. There you go. That's all I got. Anyway, all right. So now let's make predictions of words. These are the most exciting thing, right? We've seen perhaps, in like a generation in terms of what they're capable of. So in this case, our input text is not a set of handwritten digits and whether it's 7, 8, 9, 2, 3, 1, 0, whatever. Instead, it's the collection of all words on the internet and how they're used with each other. And the transformer architecture and attention concept, which is from that famous paper by Ashish Baswani, called Attention is All You Need. I think there's quite a few. Ashish Baswani plus a bunch of other authors. I think that's right. That is about this transformer architecture that allows a more optimized interpretation of the corpus, the body, the collection of text on the internet. That allows you to capture it in numeric values, numbers, attributed to each word, and the relationship of those words to all the words used around them. So, for example, cat and kitten will have numbers that are pretty similar. They'll have collections of numbers that capture their association. Cat and kitten, they're used by their usage in the collection of words on the internet. But also, if we have a phrase like, I love my ginger cat, it's also going to attribute importance, some numeric value, some number attached to the importance of the word I, of love, of my, and ginger to the word cat. Is love really important to understanding the word cat in that context? Is ginger really important to understanding the word cat in that context? Is I really important? But not only that, but all the words around it in that sentence and how cat is used in every possible situation in the body of words on the internet. The model then captures what words mean by how they relate and how important the words around them are across this entire collection of words, the internet, such that it can make predictions as hopefully high quality as possible of what words should follow any given set of words. And it can then compare that to the input data. It can also compare that to human feedback. So when a question's asked, a set of words is written, the predicted words, that's all they are, is predicted follow-on words in response to those first words. Do they mirror the way in which words, the collection of text, are used currently on the internet, the input data? You might assess how good is a prediction by comparing to what you might expect the prediction to be based on the input data. Sorry, you might compare based on the existing body of data. So you might take new pieces of otherwise unincorporated text and start a sentence, start a collection of words, and then predict what the rest of the sentence should look like, and then compare it again to the ground truth, the real rest of the sentence from the real data source. It's not looking quite like it. Okay, maybe we need to re-weight relative importance of different words and how they combine up as used in the input text in the model. But we might also use human feedback. How was that response? Well, makes no sense. So let's give negative feedback on that string of words as predicted based on the starting. Imagine like, I want to donate today what's the follow-on prediction of words, most likely? Well, we can use an example piece of text. I today want to donate my refrigerator to charity, maybe we only take the first half of that sentence, predict what it will say, and then compare it to that real used sentence by a new body of text, maybe latest text on the internet. If it doesn't predict well, then we need to improve our model and understand better the importance of relative combinations of words. We might also just have the user respond to the prediction. I want to donate my, let's say it makes a prediction, I want to donate my house to charity today. The user goes, that's not very likely, bad prediction of text. And that will now feed back into improving the model to better capture how words are used by humans in the corpus, in the body of text. What's remarkable, though, people, is that what is essentially prediction of next word based on existing use of words, gives you a fundamental model of how language is used. The point that it raises philosophical questions about what is intelligence, what is knowledge, linguistics has wrestled with these ideas. I mentioned my professor, a mentor, Andrew Parker at Oxford, who worked on trying to model human language use as a computational neuroscientist in the 1980s, trying to capture structural models. Think Pinker and Chomsky wrestling with how are there universal rules of grammar that you can capture in a computer. If this, then that, use this, then that, set of rules. And it turned out it hit some dead ends. And then along comes these bloody large language models, and they capture our use of human language via the prior set of use on the internet, all the text and how it's used, and it's able to make inferences implicitly based on maybe underlying rules of grammar, but by purely percentage likely next word that fits based on prior use in the collection of human usage on the internet. That raises profound questions for what is human language. How does it tie to our knowledge, to our intelligence? And those are things that are being wrestled with right now. And of course, I think we all think it's fascinating. What word is most likely to follow? The previous combination of words can then predict, today's wheel data, what my dog, very likely cat, not refrigerator, impossible. And again, but what happens is these emergent abilities. As you start to capture the importance of how words are used on the internet, or we heard the term multimodal earlier, how images relate to words, how we can relate between different structures, images, words, actions, choices within a digital system, we start to, based on prior use, make predictions that are accurate to us as users, but that never previously had been seen. And that comes back to the point I made earlier about this effort, originally these large language models, early effort being to improve translation. Not every word has a like-for-like use translated on the internet. Not every word has been previously translated between every language by a human. There's not like a poem between Swahili and Portuguese, in which every word has been like-for-like translated by a human. So can we capture via use the implicit translation between two different languages that maybe have limited translation between them, limited translated text side by side, just by the use of the language? But that allows us to make predictions about the translation that are strikingly accurate between words that have never previously been used side by side. Never previously have they translated the Swahili word for, the Swahili phrase, my Lego castle from the 1980s is preferable to today's, into Portuguese. My Lego castle from the 1980s is preferable to today's. They've never previously been, and yet the capturing by use of all language, from that emerges the ability to make that translation. That one even may be followable. What about emergent ability to rhyme things, find rhymes, find other even mathematical insights? This is what's so fascinating, can generate new code solutions, generate new actions. That's what's so exciting and fascinating, right? We're all, blown away by that. The more of the uses of each word and or pixels and in multimodal models, the more of each that is captured and the way its importance is, because you can go further than just say, how is this word used in relation to these words around it? You can talk about how each subcomponent of the word is used in terms of relation to words around it. You can talk about how whole phrases, and every one of those can be attributed different importance, different weight for making good predictions about the next word to use. And the model can try all those different weights, and those are known as parameters, the different importances, and you can scale up to billions and billions of those relative importances being assessed and compared across this vast body of text. So there we go. Grand costs, potentially, as we've heard. Musk has launched his new one with billions of dollars. Altman and Microsoft talk about a model that will have, $100 billion cost to develop. We can't do that every time we get new data. We can't do that for our own desire to make predictions about text specific to our company or to our own email collection or to our own. So what do? We fine tune. We use the existing models and then we adjust them. And there's a whole range of ways of doing that. Some is just using the context. You've heard of this term, meaning the input text that you pass to the existing model for a new example and say, hey, here's some information. Use this when I'm making, interacting with you as a model ongoing. That has limits. Other ways are to use fine-tuning techniques. In fact, there's an open source version of Meta's leaked Llama AI 7 billion parameters model that's made by Stanford called Alpaca. And even these are getting, these get moved past quite quickly. That was what was used by the data science machine learning research group at Codesmith to build a custom chat using both the using both the Alpaca model fine-tuned with already chat data, because it's a different type of interaction, different type of prediction you want in a chat, and though Harvard Law School's negotiation data. This was done in partnership or working with their team to build custom negotiation copilot using collection of experience and data from prior negotiations. So that did not require retraining the entire Alpaca 7 billion parameter model, but instead just fine-tuning, tweaking the existing model. You can do that with tasks, with actions like content from applications like Office. Actually, even ChatGPT has the whole way through been a fine-tuned version of their primary GPT models. The 2020 one was called Text DaVinci 003, but these evolve, fine-tuned with specifically chat data, because you've all the internet text and you can make good predictions of the follow-on text, but you want to make sure it's particularly customized for correspondence, for back and forwards discussion. And you can even do it with your own data. This would be an exciting thing to explore. We heard from Verma, I think it was earlier, Varma, sorry, who was saying, well, how would I do some experiments myself? This would be my first project would be go and fine-tune maybe Alpaca 7B that is available openly. You can do this in platforms like Hugging Face, where you can easily spin up models and then work on fine-tuning them even with your own data. That would be my first kind of project to explore. Okay, almost there, people. Final slide on this. What about predicting pixels, including streams of pixels, including not pixels, but sound waves? I don't know, digital sound. There are a whole range of models, and every day new approaches emerge. It's the Wild West and exciting for it. But I hit on a few of them here that are particularly useful for generating not words, or at least the numeric value behind words, not categories 9, 8, 6, 5, 3, whatever, but instead generating new pixels. There are a whole range of ways of doing this. I'm going to give like a hand-wavy explanation of a few of these. We first started getting excited, right? Well, actually, we've been excited about neural networks for 10, 15 years. I remember first trying to explore them 10, 12 years ago with the Grokking AI or Grokking Neural Networks, but it was a really great book. But one of the things that really brought it to attention, diffusion models at least, well, it's not diffusion models, they used GANs, we'll see in a moment, adversarial networks, was the site thispersondoesnotexist.com. In fact, I sometimes have fun when I'm on Upwork or other platforms to assign roles or tasks or whatever, to sometimes spot when I low-key think this person does not exist. I'll put it out there. There's a lot of them. This person does not exist.com, you would open, refresh, and it would generate an original human face, never before seen. How was it doing it? Well, the way it would typically be done now would be a diffusion model. Then actually they used a GAN, but we'll see that in a second. Diffusion model, it's so incredibly clever. It takes a huge collection of images, which are just faces, let's say, a class of image, in this case, face, human face. And all that is a collection of, like a spreadsheet, zeros through whatever the way the image is capturing color, red, green, blue, all the way through to across the spectrum of color for every single pixel. That's all an image is. If you look closely, it's just a collection of little dots, each of which has a numeric value of 0 through whatever, the number at which it's fully black, fully white, or fully red, fully green, whatever. So that collection of pixels, those collection of images, each of them, and there may be hundreds of thousands of them, has noise at random pixels applied to them progressively until it is entirely unrecognizable as a human face. The model at each stage is able to recognize which are the moments of adding noise at which recognizably discernible image of face, nose, cheek, whatever, start to become unrecognizable, such that it can take new, let's say 50 by 50 collection of random noise, apply that model in reverse, because the model has within it the moments and the importance of collections of pixels that represent the different aspects of a human face that, hold on. I do know. That enable, when it runs in reverse, it to apply all of those features to an original set of random pixels by taking a bunch of faces, images of faces, and then applying randomness to each random pixel's noise, like a TV, random, until you lose, the model can't recognize that bit is, a nose, that bit is a face. It's learned all the characteristics, combinations of pixels that are consistently in images of humans, faces. Consistently, they have a certain interesting combination of pixels that forms the shape of a nose. Consistently, they have a certain interesting combination of pixels that forms the dark shadow here. Certain combination of pixels that forms the shape here. It's by removing those, by randomly generating pixels across each of those images of faces until it's not recognizably a face at all and just random noise, it's learning all of those characteristics, the universals across all of them, so that it can then take a whole original collection of random noise, apply in reverse all those universal pixel collections, the universals, to that random noise and produce a brand new face. That is very, very cool and very hand-wavy for me. But at its core, the model learns the core characteristics, and as you remove them, it identifies when it becomes random and loses the sense of recognizably core characteristics. Now it has the sets of pixels that represented core characteristics consistently across a range of different faces, so that it can then, on new random noise, completely like a random set of random noise, right, different to ones we've seen before, it can then apply all of those and generate out of that new faces with all the key characteristics of a human. Other ways to do it. Conditional variation autoencoders there, CVAs, a different approach to it. They, similar but different, analogous, take images of faces, dimensionally reduce them, reduce their dimension, like take them down from, keeping it simple, 100 pixels by 100 pixels down to 5 pixels by 5 pixels. That 5 pixels by 5 pixels, and then scale them back up to the full image of faces, trying to minimize the loss between the, sorry, I'm getting tired, They take a bunch of pictures of faces, a conditional variation autoencoders, take a bunch of images of faces, 100 pixels by 100 pixels, 1,000 pixels by 1,000 pixels, whatever, and scale them down to lower dimension. Let's say, keep it simple, 10 by 10 pixels. They then try and scale them back up, minimizing the loss. That means it should look as much like the original unscaled down, unencoded, decode it to scale it back up, should look as much like the original as possible. In doing so, you want that 10 by 10 image to have as much of the distinctive information about that person's face that is not consistent across all people's faces as possible. But that means the model should contain within it as many of the distinctive things, the universal features of all those images, faces, in the model as possible. You want to capture as much of the information that is universal to human faces in the model. And then in the shrunk down one, only the things that are absolutely only essential to that person's face, if you want to minimize the loss when you scale back up. Well, now you could take a new random 10 by 10 collection of pixels and apply the scale up. And that model's got as much of the essential information about what makes a human face in it as it possibly can. Meaning you can take that 10 by 10 pixel collection, apply it, scale it up, and you get an original face with all those key characteristics of a human's face. All right, adversarial neural networks. Let's briefly touch this for a second, because I know we're getting late here. Thank you, everybody, for sticking around. Very, very generous of you. So, adversarial neural networks. Two models. One is a classic, much like here, categorizer. It takes in an image of, in this case, it would be a 9 or an 8, and determines likely by attributing different importance to each pixel. When we use training data, it takes in, it takes in 70,000 images of, why don't I just use exact example? It takes in 70,000 images of cats, and they're all, and I know, I'm sorry, let me say 100,000 images, 10,000 of them are cats. They're labeled cats. It tests different importance to different pixel combinations that best predicts for that set of data as many of those cats correctly as cats. That's your model. It then gets past a new cat image and it says, yes, that's a cat. And a new dog image goes, no, that's not a cat. There's your cat predictor. A separate model, its job is to generate random squiggle. It generates it. It passes it to the cat model. The model identifies cats, and the model identifies cats, but obviously that's not a cat, it's a squiggle. I didn't say it's squiggle, it's just not a cat. The model that is generating random squiggles keeps iterating on generating those squiggles with the goal of persuading the cat identifier that this picture it's generated is a cat and not a squiggle. And it does so until it's able to persuade that model that what it's produced is an image of a cat, at which point it has produced an original image of a cat. These models compete with each other, one and the other trying to get better at identifying fake cats so that the model that is generating random pixels or squiggles that is trying to make it pass the other one, generate a cat, gets better and better until it is able to persuade the cat model this is actually a cat. Well, at that point, it's generated an original image of a cat. There you go. I'm moving the right screen. Text conditional image generation, which is what, I see every bloody Codesmith person in their background has like some funny generated image off DALL-E or whatever, from OpenAI or Midjourney or any of these image generations. They are also using a model that's mapped text description, we talked about it earlier, to image across the corpus of the internet, or images and corpus of text on the internet, so that you can then capture a description and then generate pixels based also on that model that associates text descriptions with pixels. Where do you get that data to train that model on? Google Images, every alt text, that's the right click, that's the hover over text on every image. And then also there are non-profits even, there's a big one, I think in the Netherlands or Germany, that just produces that raw data as training data for machine learning models. Oh my goodness. Okay, so trying to keep it very tight here at the end. This introduction of groundbreaking prediction. It's all still using prior data to enable you to make good, accurate, hopefully, predictions about new situations, whether it's what the user's going to purchase or whether it's the text that best continues based on the pattern of text as used on the internet, the phrase you started, or the question you've asked, the text that best continues that as an answer, based on the collection of use of text in the history of the internet. These predictions are changing our whole world and lives. They have to be integrated into applications. What's the team that builds that? Well, there's data scientists. They make the prediction good. That's known as the model. They got to understand the math behind it. They got to understand the research papers. Their time is spent looking at the latest research papers, reading up on, okay, how does someone deal with that situation with this type of data? They're building a prototype of the model, by the way. They're doing it with smaller case sets of data, often on their own computer, to try and work out what the right model to even apply is that gets the best, gets towards the best prediction. But that prediction is potentially very slow, very, very expensive to make. And if you want to update it, my second talk today, I had a student workshop during the day in the morning. So that prediction, expensive, got to give a ton of money to NVIDIA. Congratulations to NVIDIA for having, what was a 60% margin in the first quarter of this year? What did $25 billion revenue, $15 billion profit? What was it? Hey, is his name Jensen Huang, I think? Maybe you know the name better, but as far as the founders go, he seems quite nice. Anyway, we want to make it cheaper. We don't want to pay NVIDIA too much money. The ML engineer's job, make that prediction fast, cheap, up to date. That is to say, when the user gets, so let me give you an example here, lex.page, let's make it specific. Lex.page is like a text editor, like a Google Docs that gives you some AI feedback. So you can start writing, like Google Docs does, but more focused. You can start writing some scrappy text, and then you want to press a button saying, make it posh, or make it funnier, or make it more relaxed, whatever. The data scientist's job is to make that prediction, the posh text, accurate. How does it do it? Well, there's a number of ways it can do it. One is like-for-like pairs of messy text and posh text, and determining what are the most important characteristics of the messy text as predicting producing the posh text. That's a data scientist. They'll do that with a smaller set of examples on their own computer, potentially. The ML engineer says, aha, great job. We found the right model. It's making a decent prediction. Now, shoot, if we want to do that for a lot of users, and we want to do it for all edge cases, and we want to do it without it taking a ton of time and cheaply, you're going to need my help. They're going to have to understand both. It's why the ML engineer job is the most interesting job perhaps in the world right now. They've got to understand the nature of the models, that's the math and the research, and the nature of computers, because they're going to distribute that task across lots of computers. So if they want to make it fast, they need to know if we make it a little bit less accurate, it's going to be 10 times faster. They've got to understand the nature of the prediction, the model, what's the math behind it, how's it really working, and they need to understand how they can distribute that across a same set of computers as efficiently and performatively as possible. That's a fascinating job. A lot of Codesmith grads take on that job sort of 1, 2, 3 years out. You get really good at engineering. And honestly, right now, you probably do a data science master's, combine it up, ML engineer. What I describe out of Codesmith, we'll see in a second, is, okay, great. Now you've got to integrate that prediction in an app. And that doesn't just mean build the app. That means integration of that prediction. So what's that look like? Well, particularly it means helping deploy the model that's going to do that prediction online. That means things like containerization, having it run on AWS. That's no different, per se, to having any server running, any code running on the internet. You're potentially, as a software engineer, the expert in that, but you're going to need to understand the nature of the model enough to help the ML engineer do that. What about the API design? Well, what about the data pipeline? As a software engineer, let's think about lex.page. The user writes their messy text, says, make it posh. Hopefully back comes posh text. The messy text has got to be pre-processed. What's it going to look like? That's going to be passed to the model in a structure that works for the model to look at. It doesn't just take any old text. It needs to look at it. It needs to be structured and have metadata, have maybe information that maybe there's other factors. that help make the model more predictive, like which bit of the text did the user just edit? Which bit of the text, you see what I mean? Those factors matter in making a prediction good. The model can be improved based on that. You as the software engineer at the intersection with ML engineers, at the intersection with it, are an important contributor to designing that architecture well, designing that data pipeline. You're not a data engineer, you're a software engineer who's got to work with a bunch of data. Their company may not have a data engineer, likely doesn't. But you're working right at that interface there. It's really cool. What about the fact that the user edits the text that's posh generated and makes a bunch of changes? That's really helpful information to the data scientist to improve their model, to improve their prediction. You got new data. The user actually live edited the prediction and made it better. Great, improve the model of that. But at which point do you snapshot the user's edits to pass back to the data scientist to improve the model? I don't mean literally snapshot, but like at which point do you, well, I do, I guess, hold that text, store it, hold the next change. These are all things that to understand how to do it well as a software engineer, you need to understand enough about the nature of the models and the model pipeline that you're working with. That's why that's all now in the Codesmith curriculum, because it makes you a better software engineer at the intersection with the ML team. And then finally, build the rest of the bloody app around it. Like my favorite app that I use a bit is called Suno.ai that lets you describe, write me a reggaeton song about Codesmith, a coding school. I love it. It's so much fun. The coolest bit maybe is the prediction of the sound waves, but you've got to build the whole app around it. Now, here, there's also some new tools available, the code pilots, the agents, but understanding how to use those well as well also can benefit from understanding how the LLMs are built under the hood. But even more important now in the rest of the app building is a readiness and ability to problem solve whatever the tool is, because the problems that you can work out with these sorts of new emerging tools get even bigger. You can start to try and tackle as an engineering team, as I say, hospital healthcare integration, like things that have never been tackled before, like, I don't know, integrating vendors and, you know, doctors' recommendations and pharmacy benefit managers in a healthcare system. You can start to tackle those now. The prediction is made by the data scientist, made it good. The ML engineer makes it fast, cheap, and live. And well, live, the software engineer helps as well, but at least, you know, they work with the software engineers. The software engineer integrates that prediction in the app and helps keep it live and up to date. And then the rest of the software engineers build the whole app around it. It's pretty cool that Codesmith grads can stand out in this bit here with the new curriculum, and all the alumni get this as well. So there we go, people. So what's your next steps? Firstly, recognize as a software engineer, problem solving and technical communication become way more important when the scale of the problems being solved are in healthcare, finance, agriculture, energy, government, and not just e-commerce, which has been a major part of, you know, software, right? Much more and more, it's the core piece of society's problem solving. But some new domains. So build out your mental models in, and this is stuff for alumni, sorry. Building, but there's an LLM hard parts coming. As I say, in the next few weeks, look out for it. There we go, people. I went way over. I am so sorry for being grossly over. Let's see if there's any additional comments in here. If you want to, oh, what am I talking about? I gotta push a few things. Okay, apply to Codesmith part-time program. The deadline, the early admission deadline is Friday to be considered ahead of others. The regular admissions deadline is next Friday. Yeah, okay. That's the part-time program, 9 months long. Go to an info session, I guess. Go to the LLM hard parts. Sign up for events to see when the LLM hard parts comes out. I think it's next week. You're welcome to connect with me and ask more questions on my LinkedIn. There it is. There's my LinkedIn, or follow me on Twitter. How about that? Look at that. I'm even trying to do Twitter now because my partner is very encouraging of me doing it. There we go. Let's see any other comments and questions here. Fern, great. Right, exactly. Yes. Fern points out that adversarial networks, and that is the nature. These things appear magical, but associated with the magic is the black box that they represent. Exactly how to tweak and prevent those sorts of difficult edge cases are wildly challenging problems. Yeah, that this person does not exist is fascinating. Yeah, Varma, good shout. Yeah, I just really encourage you to come to the LLM Hard Parts Workshop. Yes, also from YouTube. Alexander, thank you, Alexander, on YouTube. Yay, thank you for joining. Let's see if there's any other questions on YouTube. Oh, we probably should make sure it's muted, right? Oh, great. Good chat. Thank you, people. Shout out to our YouTube fellas. That sounds like a gendered term. Our YouTube folk. Shout out to our YouTube folk. Great questions from Rakib, Alexander, Vladimir. Yes, Vladimir. Why was this question not passed through to me? This is the most important question of all. That is the question here of Vladimir. Yeah, I'm in Mexico City. Yay. And I was sharing early this morning, my Spanish is getting better, people, but my Spanish primarily, let me just stop sharing a second. My Spanish primarily still is learned by going on Maria Becerra and Carol G's Instagrams, where I learn the captions. So the one I'm learning right now is I want to thank my friends, my family, and my fans, which I think is not going to be very useful. But I did also learn. This is my best one. I used this morning, so I feel like I'm showing. I feel like I'm showing off. Desayunito nutritivo. Si yo soy el aperitivo. That means nutritious breakfast if I'm the appetizer, which was shout out to Carol G for that one. So obviously working, and other ones I've learned. Las mejores cosas de la vida y las más reales, las mejores cosas de la vida y las más reales nunca quedan grabadas. That means the best things in life and the most real are never recorded. Again, shout out to Carol G. Anyway, all right. So, yeah. Yes, good shout. We've got here me low key. You can also fine tune with retrieval augmentation. That means you can go and retrieve more data live in the model's execution from API calls. So shout out to me low key in the chat here. You can fine tune it for function calling like APIs. Oh, did we lose our? Yeah, we are live, right? And yes, RS there, who presumably is a familiar friend. Yes, there's an LLM hard part starts in the next couple of weeks. I think we leave it at that. You've got my, you can also feel free to email me, but I know people tend to want to do it on like the social apps now. I'm really looking forward to the LLM hard part. Shout out to James Hunt on that. Thank you everyone for joining all around the world. Fern, great question. These are the sort of things, visibility on the predictions, on the model's workings is all part of the latest research, particularly in safety and alignment. And maybe you saw that the safety alignment team was disbanded at OpenAI, and the leaders of it have moved to Anthropic, which was already a spin out of the team of OpenAI that are more focused on alignment and safety. One of the big things they look at is understanding the reasoning process, not reasoning, but the process by which predictions are made. Without understanding that, which is a very, very difficult thing to resolve, it's very hard to make improvements or make recommendations on the strength of the prediction, for example. So these are the kinds of wild and fascinating research areas happening right now. Thank you, Kenny. Thank you, everybody. You've got my contacts there. Shout out to Fern for great comments, contributions in the chat, particularly shout out to Fern there, like great comments. And hopefully see you all next week for whatever is on the events docket next week, which is next Wednesday. Wait, is it the same talk? Did I do the wrong talk today? Shit. software engineering in the age of AI. Next week's is AI for software engineers. Oh, okay. It's more of a deeper dive on some of this modeling stuff. So we'll actually start talking, we'll build out Lex.page and think about what models might have been used to achieve its predictions. That's next Wednesday. All right, people. Thank you, everybody. Good luck in your applications to Codesmith and good luck regardless. Thank you, Emilio. Thank you, Fern, Kelly, Tim, and Kader for being on video as well. I appreciate it. Cheers, everybody. Bye.